Okay, coming up next, like all great movies, last year's USB talk gets a sequel. And are you gonna turn it into a mini-series? Anyway, in case you missed the first one, don't worry. You should be able to enjoy this one as well. And if there are jokes that you don't get, well, that's why you should have come to the first one. Anyway. USB, how does it even work? Version 2.0. Does the first one have a version, or are you going to rename it retrospectively?
I guess we'll rename it.
Yeah, well, that's the thing people do. Next, please welcome MacLemon.
Oh, thank you for coming. Yeah, I'm MacLemon. You can find me on these interwebs. If you want to ramp about this talk, please use these hashtags, BalCCCon2k23 and USB, what the fabulous thing it is. Who of you has seen last year's talk about the beginnings of... That is quite a bunch of hands. Okay. So yeah, that was USB. How does it even work? If you haven't seen it, there's the link, there's the QR code. I'm quickly switching over so you cannot scan it. And here's the brief, flashy summary that too long didn't watch of it. So last year I sat here and said, well, the missing parts would be a problem for future me and a future talk. So that future is now, this is that talk, and I'm still me. So what was before? We had these type A and type B micro and mini variants of connectors. We talked about the USB 3 super speed type of connectors with not only 4 but 9 pins. They came in this nice blue, and then they came in this nice teal. This was USB 3.1 generation 2 super speed plus, and then they came in all the colors, and yeah. But in the end there can only be one, and it's this. I present you the reversible USB type A connector. It's the permanent quantum state of it goes in. Not the one you're looking for? Okay, oh, the other end. The reversible USB micro B connector. You can flip that around. No? Okay, you're not convinced. How about that one?
Yes, I have that one.
If you follow me on Mastodon, you might have seen this is the solution. It can change state. So yeah, you did not expect that one, I guess. No, but seriously, Highlander. There can only be one, and that is USB type C. That is the official term. So let's start with what does make a USB Type-C connector or cable. There's a lot of specification, and this defines the plugs and the wires and the receptacles of these connections. It does not imply any functionality. Yeah? Okay. As usual, USB stuff comes in revisions. The Type-C cable and connector revision 1 point something. Like 1.0 to 1.4, they were used for introducing Type-C into the USB 3 standard and retroactively allowing its use for USB 2.0 without renaming it. Version 2 of that specification introduced USB 4. That was basically it. And version 2.1 added extended power range for power delivery. We will be talking about this. And 2.2 is the current revision of this thing. It was released in October 2022, meaning just right after last year's BalCCCon. And it includes a few new, very interesting changes. So let's look at the pinout. These things are very tiny, so the pins are also very tiny. The receptacle, that's the thing on your computer or your phone where you plug something in. It's got 24 pins. This is a so-called full-featured connector, meaning everything's connected. This is a term specified explicitly in the specification, so nobody can call a full-featured cable without implementing those pins. It's got 2 rows. At the top, there's the bank of row pins, top A. At the bottom, there's the row B, and the numbering scheme is clockwise. And there's 4 pins for ground. These are all connected up. There is V bus, which means this is where power comes in. Yeah? This is the plus side of things. In the middle, you have the D plus and D minus. If you remember, those are the differential data pair pins used for USB 2 connections. There's some transmit and receive pairs, 4 of them in total for USB 3 and 4 data transfer speeds. And there's a site bus, which is also very interesting, used in alternate mode. And to complete things, the final pair is CC1 and CC2. They're used on the configuration channel, which is very important for USB 4. So yeah, that's the whole thing. How does a receptacle, now this is the receptacle? Yeah. How does a plug look like? Well, it's basically the same thing, just the numbering is counterclockwise now. And there's a few tiny differences. The CC pin is not called CC1, but just CC, the control channel. And the CC2 becomes a VCon, like voltage for the connection, for the local connection, so you can power the cable itself. And the D plus and D minus pins are only on one half of the connector. You already may be thinking about, but you could probably, and how does this work? We'll see about that. So if you put them next to each other, that's a huge bunch of labels and nobody will read that anyway. So what's possible with all those pins? They can do a lot. They can do USB 2, they can USB 3.2, they can USB 4, they can deliver power, a lot of power, and they can be electronically marked, which we'll see as well. USB Type-C cables are quite a complex beast. I mean, there's a lot of wires and a lot of pins. They need to go into that cable. This is what the specification tells you. This could be a cross-section of such a cable. That's not really interesting. This is a photo of a cable. This is what a cross-section actually looks like. You can see the pairs of data and power, like the ground in the center and the red one to the lower left. And this is a different cross-section from a different cable. That looks quite different. It's a more premium one with coax data lines. Thanks to TubeTime for providing me with these photos and letting me use them, because they're awesome. So what can we do with this, and are we ready to plug in a cable? So if we take a USB Type-C high-speed cable, high speed, that was USB 2.0, 480 megabits a second. And that is what these pins and cables do. They can provide 900 milliamps of power, which is not a lot at 5 volts. This is inherited from USB 3, so there's a tiny difference here. And you may see such a receptacle, for example, at a microcontroller board or a conference badge. They actually do USB 2 over a Type-C connector. Then there's these fancy charging cables. They do not do any data. They don't have USB 2 data or 3 or anything else. They just charge. Yeah. Apple at some time provided laptops with a charging-only cable. So no data on those. I'm not sure if they still do this, but they carried like 60 watts of power, 100 watts of power. And how would you distinguish all these cables? Like, you look at a USB Type-C cable and cable on the wall. Tell me what you can do. No way. There's basically no way to tell. So yeah, you should get a visual cable distinction. And the specification tells you, yeah, these should be somehow identifiable. And we should improve accessibility for those cables. So what did the USB Implementers Forum do? Well, everything needs a logo. We know that already. So they introduced new logos for packaging. They come in this nice USB red and blue with the cable on it. It contains the maximum speed capable of that cable. So if your 2 devices can do that speed and the cable can do that speed, they should be able to actually transfer data. It also comes with a power rating, for example, with 60 watts. And this logo would be on the packaging for the cable you buy. On the plugs, you should also have a designator. It's basically the same, but a little smaller because plugs are small and they get hard to read. So they improved on accessibility, which is nice. A more premium and special cable would have like 240 watts of power delivery and 40 gigabits a second. or maybe even 80 gigabits a second. I already see people like, oh, never heard of those. Yeah, but there's more logos, and they come in variants, so there's no speed designation on these, for example. They only come with a power designation. That means they're either charge only, or they are called what is a high-speed USB Type-C cable. High speed meaning it's the slowest speed other than none at all that you can buy. So if you see a cable that only has a power rating, it will do USB 2 speeds or none at all, but it will do charging with this thing. So at least now you know. The configuration channel. We already heard about it. It's important. Just 2 pins. It's used for discovery and configuration and management of the connection. It's mandatory. So it's also used to determine the orientation of the cable. So you can plug in a cable like this, or you can flip it upside down, or you can twist it. So your cable can do the dance moves now. And it also assigns which of the transmit and receive pairs go together, because if you flip it around, we'll see what happens. So these are the 2 pins, and they're connected through. And on the other side, one goes to the CC channel, and the other one goes to the connection. So the pin can be reassigned and will power the cable, actually. Why do we need that? Because some of the cables are electronically marked, meaning there's a tiny chip in there, and that needs power. And the computer needs to know what the cable will talk to and will do, so it needs to power that thing. So how does the configuration channel work? On a device that provides power, it pulls up the CC pins with a resistor, like applies power to them. If you're a USB device that consumes power, you pull them down, and the host monitors those 2 pins, and depending on what they do, it knows, hey, something has been connected, so it can detect an attach event for those cables. It's also used to resolve the cable orientation, like which way is up. Of course, we know the only way is up, but not with USB-C. And it also establishes the data roles for power and data pins. It uses this to discover and configure the V-bus, so meaning like how many volts do we apply there? Do we apply any voltage at all? Is it needed? And it's also used to configure alternate and accessory modes. We'll see about the alternate modes. Yeah, so if you want to do USB charging and power, you know the problem. USB provided 5 volts with 100 milliamps for small devices, or 500 milliamps that became 550, and a whopping 900 milliamps, meaning 4.5 watts. With phones and batteries becoming larger and larger, the time to charge your device would become longer and longer. And if you don't forget to put your cable on the plug overnight, you don't need fast charging, but if you do, it comes in really handy. So people demanded more power. The vendors thought, well, we can do this. Here's a brief overview of all the proprietary versions on how to fast charge over USB. You're not supposed to read this. It's not really helpful. It's just here to illustrate, like, there's a lot of different variants of those. Some are licensed technologies by other vendors, so they come with the same technology, but a different name or a different branding. Some versions are compatible with others in some versions. Some require special cables, like a USB Type-C cable that has things that are not Type-C. Some go way over 6 amps, like over a tiny cable, 6 amps. That amps is what makes cables go hot. Yeah, so you would not trust any cable with that. And if USB wasn't already confusing enough, well, charging or fast charging can leave you frustrated to no end. So the solution in the style of the implementers forum would be, let's get all the vendors do the same thing, like, yeah, this is gonna happen, sure. And it'll be quick, because everybody will agree immediately and not try to defend their own proprietary stuff, sure. But they came up with something, and if you have USB Type-C, you can actually do 7.5 watts easily, which is already quite a lot, and you can even go up to 15 watts. So for users, it's still a terrible mess, but if you don't forget to plug in your phone at night, this is not really relevant. But we can do better. We can do USB power delivery. It's not as new as many people may think. It started in 2012 actually already, with very little fanfare. It was specified in revisions, of course. 1.0 delivers already up to 100 watts, which is more than the proprietary versions could deliver. And it was backwards compatible with USB 2 cables and the standard battery charging specification. So you could already charge batteries pretty quickly with that and transmit power and data at the same time. It came with a bunch of profiles that specified like the voltages and how many amps it would do. The exact numbers are not really important at this moment. And it would do this over standard A and B connectors. With a B micro connector, it would only do 60 watt because that tiny connector is only specified up to 60 watts. And I'm not sure why they made 60 watts go with a tiny thing, because it will get very hot. Power Delivery 2.0 is basically the same profiles. It was introduced with USB 3.1 Generation 2 Super Speed Plus about the same time. It added support for the new Type-C connector. For control channel negotiation, we have already heard of that. There was an old method for the older connectors that was still supported as a legacy, and it supported the cable ID function, that is this electronic marking. And it also does alternate mode negotiation now. So we can go up to 20 volts and 100 watts now, like at 5 amps. And normal cables are rated up to 3 amps. If you go over that, if you want to deliver more than 60 watts over a cable, you need to have an electronic marker that tells the devices, yes, I can actually do this without going up in flames. So it's a safety measure for users, and that is a really good idea. Power Delivery 2.0 Revision 1.2 replaced the profiles. They were fixed with power rules, so they would allow more flexibility when charging, and the voltage levels where it used to just 4, now there's 5, 9, 15, and 20 volts. Okay. But with Power Delivery 3.0, things changed dramatically. It drops the support for old connectors, like A and B are now gone. It's Type-C only, and we have that Highlander moment again. I mean, after all, there were multiple movies by that name, and in the end, there can only be one. So it introduced a very few nifty things, like a programmable power supply, or PPS. It's optional, but it allows a more granular control over the voltage levels, meaning you can go from 3.3 to like 21 volts, very tiny steps of 20 millivolts, and it allows a device to exactly tell the charger how much voltage and current it wants to optimally charge the battery. So this improves lifespan of your mobile devices, actually. It's a nice thing to have. If your charger supports PPS, you will get a new logo. And it's the certified USB fast charger. The most important thing, meaning the power rating, is also the thing that's printed smallest and gray on white. So it's the hardest one to read, but you get the fuzzy feeling of having a fast charger. But only if it supports a programmable power supply. It also brought authentication, meaning 2 port partners can now authenticate with certificates and digests, and it will actually protect itself against replay attacks. So yeah, that's its own specification with over 100 pages. I will not go into any details here because it's authentication, and that is always interesting. It also supports fast roll swapping. A power roll means, hi, I can provide power, or I would like to get power, and USB can swap those roles. Your laptop can provide power to a device, but it can also receive power for charging. So you can swap those roles. And with power delivery 3, we get fast power roll swapping, meaning there's less interruptions of power when you actually change those roles. So that is handy because your devices will not go unmounted automatically if you have a dock and you just plug in the power to the dock, because there's a lot going on in the background and you don't want your connections to drop. Of course, as everything with USB, power delivery comes with revisions. So power delivery 3.1 in revisions 1.0 to 1.8. Yeah, it adds a few things for stability, edge case handling, more reporting on how much power is being drawn. And it also provides more power than 100 watts, meaning you can now power your gaming laptops and workstations. You can charge your electric scooter with this. It goes up to 48 volts at 5 amps, meaning that is 240 watts over a USB cable. Yeah. Remember, amps make cables go hot. Voltage makes cables go sparky. And with this extended power range, a cable must be electronically marked, meaning the cable must explicitly opt into this, like, yes, I'm really sure I can do 240 watts. And these cables are quite of the beefy type. Yeah? I can pass it over, and you can have a look at it. Yeah, any cable that is not explicitly rated for 5 amps or extended power delivery, extended power range, will just give you 60 watts. How does that work in general? So legacy USB ports had a special role. They were either providing power or consuming power, nothing in between, no shenanigans there. USB Type-C changed this. So you have a source that is supplying power. If you attach something to it, it assumes a data role, meaning downward facing port, like, hello, I'm talking to you, and it provides power to the cable that you just plugged in. If your device is a sink, it consumes power, and if you attach to it, it will use an upward facing data role, meaning like, hello controller, talk to me. And there's dual role power ports, like, for example, your laptop, it can do both. And each connection and power delivery connection is between 2 port partners. USB power delivery is quite a polyamorous system. There can be multiple devices, but each is connected via their own separate port, forming their own unique relationship between those port partners. And only one at a time. Within a relationship, only one of them can be a source and one can be a sink. And with dual roles, that is subject to change. But like in any good relationship, that requires communication and negotiation capabilities of the source, what they can provide, and what the sink needs or requires. The same goes for data roles. So, architecture, how do we build the thing that does all these things? There's many layers involved, and dual role devices need to implement both of the things that I will show you now. It's getting a complicated diagram, but we build it up part by part. A provider can also have multiple source ports, meaning you have a charger with multiple charging ports, and they can either share power across ports, or they can dedicate power to ports, meaning this one always delivers 60 watts. Or you can do another rate depending on what is connected to the other ports. So you can do a little household calculation there. So on a provider, we have a device policy manager. It deals with the power resources, meaning how much can this thing actually do in total. It applies a local policy, and for each port, it interacts with a policy engine. That's a policy engine. That is part of the individual port already. The policy engine allows for negotiation and establishment, an explicit power contract, it's called a contract, between the port partners, and if that contract is accepted or refused depends on what the policy manager tells it because if they want to get 100 watts and the policy manager says, well, we only have 60 available, you've got to deal with that. And then the port can only do 60. There's a protocol layer involved. It handles the message construction, message flow, the detection of communication errors via CRC error checks, and it sends and receives those messages over the physical layer of the CC wire. And there's also a port controller involved, which handles the actual interaction with the port. And being a power source, well, we need a power source, of course. Either being a transformer plugged into the wall or a battery if you have a power bank, for example. This is all wired up to the CC pins for communication, and VBus, meaning these pins supply power. What about a sink, a device that consumes power? Well, it's the same thing, but the battery is empty. That's basically the difference. And these two, they talk together, over the cable with each other. The CC pins are for negotiation, and power is delivered over VBus. So, we already heard about pulling up the CC lines and pushing them down to negotiate and tell you what you want, what you really, really want. And before you can do a power contract, a power delivery contract, if your battery's dead on the phone or on the laptop, it cannot do this. So it can, over the CC wires, by pulling up those resistors or pulling them down, it can tell you, well, can you just give me 5 volts and 1.5 amps or 3 amps for the start? And then we'll just start slowly charging. And at some point, your phone will boot. And it will do some communication over the CC wires now, and then start charging really fast. And the part where that piece of silicon that does the CC communication is not yet powered up is where you fall down to the older protocols to like get the battery up a little so you can safely power those electronics that you can do the communication. So this is why your phone starts charging slow when it's really dead and then switches over to faster charging. This is controlled by a state machine. It basically looks like this. Yes, it's really complicated. It's a scary beast, but it's well documented in the specification. And if that's not enough, go to one of the silicon vendors. They have really, really good explanations how this works and how they implement all of this. If you want to use USB power delivery in your own projects, like I have this tiny microcontroller thingy project I want to use, please don't try to implement CC protocol on an Arduino or so. You don't have enough RAM memory and RAM and anything to actually do this. There's pre-made silicon. You can buy a USB-C power delivery trigger PCB very easily and cheaply, and it will do all the edge cases you never thought about. And it will save you a lot of time, and it will actually work. I hear the words magic smoke. Yes, it might help keeping that in. But power delivery connections also involve cables. We already heard the term electronically marked. This is the e-marker. A full-featured USB Type-C cable shall have an e-marker. Shall means it's not a must. It'd be nice to have. If your assembly is rated for more than 3 amps, it shall be electronically marked and include what the cable actually can do. And yeah, it's a small chip inside the plug of the cable. It tells you, can I carry 3 amps, 5 amps? What about high voltage, like 48 volts? You want to have enough insulation that it's not really uncomfortable to touch the cable. It will tell you how fast can this cable transfer data, or how fast should it be able. Does it do Thunderbolt? It also does vendor information, like who built this cable. And some cheap cables, they provide an e-marker, but that shows probably some incorrect information. Like it also has an information on cable length. This one tells you it's 2 meters. This one also tells you it's 2 meters. You may trust one or the other on being So what you can expect from power delivery is in the specification, but there's also moments for unexpected power delivery. What do you mean unexpected? The annoying kinds. With some devices, the negotiation, who is source and who is sink? Well, it's a little complicated with partnerships in USB at times. So for example, if you plug in a Nintendo Switch, like a portable gaming console, into your MacBook Pro, what would you expect to happen? What would you like to happen? You probably want to charge the console. What actually happens is the Switch says, oh, I see a new port partner. I can provide power, and starts charging your laptop. At least until the Switch is completely dead, and you have to get your power supply anyway. I'm not exactly sure if this still happens with current versions of that hardware and software. I don't have a Switch to test, but either way, you cannot influence how those two interact with each other. So that's an interesting part. Then there's the case of unexpected USB power non-delivery. Huh? What do you mean non-delivery? Well, power delivery needs negotiation and a contract, and you need to pull down the CC lines to tell the source, hey, I need power, and how much you need. And the specification clearly says those two CC lines need a separate resistor each to be pulled down. But if you take the bill of materials for a device, well, that one resistor, we can save a little money here. Like very, very, very little money, even if it's 1,000,000 times. The Raspberry Pi Foundation is famous for doing this, like saving one little resistor. So if you plug in the USB-C power charger into your Raspberry Pi Model 4, it may or may not charge, depending on the cable. If it's a really old and bad cable, it will charge. If it's an electronically marked cable, CC communication will fail. The power supply will insist, this does not work. I'm very confident in supplying 0 volts to your Raspberry Pi. So it might depend on getting a bad cable to get your Raspberry Pi actually to boot. This has been fixed in current board revisions of the Raspberry Pi 4, so if you can now buy one, I heard it's getting better, this should be fixed and not be an issue anymore. Then there's also the unexpected power delivery of the nice kind. USB power delivery requires Type-C connectors on both ends to negotiate that contract. But what about different connectors? I mean, what if you had a different connector to do this handshake? Well, there actually is a different connector that's not Type-C that can actually do power delivery contracts. It's by Apple, it's called Lightning. It provides USB over a non-USB connector. And since the iPhone 5 in 2012, like over 10 years ago, Lightning connectors can actually remap pins to different protocols. And since the iPhone 8 from 2017, that's also the first one that does this Qi wireless charging, you can do USB power delivery over a Lightning connector, like standard power delivery contracts. So you might want to try that. The same is true for the MagSafe 3 connector of the new M1 Apple Silicon laptops and future devices. They can also do USB-C power delivery over a magnetic connector that's very proprietary. And since we talked about USB over non-USB connectors, let's see. There's alternate modes. They provide non-USB protocols over USB. Like they carry different signals? Really? They do, yeah. So the physical wires actually get repurposed for some other signal. Like they're switched over. And both the differential data signal lines are used for this, as well as the sideband lines. And it gives you 4 unidirectional lines that you can transfer your signals over. Alternate mode, as many other things, needs a negotiation that also happens over CC, and it requires power delivery because it uses the same protocol to talk to each other. But if you look at the time, it comes after power delivery. So the CC lines to the very top left, hey, here's a connection. We provide some safe bus power, like 5 volts at 500 milliamps. Nothing can go up in flames, hopefully. Then they negotiate power delivery. They may fall back to charging specification. VBus provides that power. It configures the alternate mode. Legacy USB starts enumerating devices and device classes. And then alternate mode negotiation happens. So your USB port from the host says, hey, device, got any alternate modes ready? And the device says, yeah, well, here's a vendor-specific defined message, a VDM with a data object that tells you what I can do and how we do this. So, okay, then the host says, well, let's enter that mode. Both switch over their data lines on the USB-C port, and the device acknowledges or does not acknowledge, like, I would like to, but something's not working out because the cable is bad, or I don't like it, or something. And if it works, well, the mode is reconfigured and the data lines are switched over. An SVID, a standard or vendor ID, it's just a 32-bit number, but it explicitly tells you which alternate modes are available from a device, like what it can actually do. But what if that fails? Like, there's this USB 2 class specifications, like I've got a camera, I've got something else, I've got a human interface device. There's also the billboard device class. And that is required for, oh, it's not required, it's a should, again. But how do you tell the user that this alternate mode for the display they want to connect does not make the display things? There's a catch-22 in here. So a device that does alternate mode should also implement the billboard device class, and that is used to display an error message, because some of the first things in USB 2 negotiation that happens is human readable string from the device to the host, like this is what I'm called, this is what a user would be able to identify me by. And that billboard class is used to somehow make the operating system convey an error message like this one device of the 27 you already have is not working for that reason. Also, the operating systems are with a should clause here, and I personally was not able to like provoke my display and computer with weird cables to actually provide such an error message. So your mileage may vary, you may get one or not. So in USB 3.1 and later, which alternate modes are available? There's DisplayPort, it was the first one, it's also the most important one. It's a specification by VESA, and you may have seen the DisplayPort connectors and logos, they look like this. And over a USB Type-C alternate connection, you can get DisplayPort 1.2 and 1.4 even with stream compression over a USB Type-C cable, full featured cable that is. It repurposes the transmission pairs actually for displaying, for using DisplayPort lane 0 and lane 1 unidirectionally from the host to the display, so they go one way. It uses the side pins, the sideband pins for auxiliary display data, like which resolutions and things can you do. And it can, in addition, use USB 2 data transfer over the same cable. And even when possible, some displays provide power to your laptop, for example, and you can even charge over the same cable in the other direction, which is really handy. You just plug in one cable and everything starts lighting up and working. This is what the plug looks like. The cables are kind of beefy in some regard. So here's a standard DisplayPort cable if you want to have a look at it. But what other connections are important over alternate mode? There's Thunderbolt 3 to be exact. It's basically PCI Express over a cable, Type-C cable. Thunderbolt 1 and 2, they used a different type of cable, which was this one. It used this mini DisplayPort connector, which was invented by Apple and then standardized by VESA. So there's this cable, and yes, there are adapters from Thunderbolt 1 and 2 to Thunderbolt 3 over USB Type-C. And yes, Thunderbolt comes with a logo, of course. It's a specification by Intel. It provides you with up to 4 lanes of PCI Express 3.0, meaning 32 gigabits a second. That's quite nice. It's got 4 lanes for DisplayPort. And the actual maximum bandwidth is 40 gigabits a second. If you want to exceed this by providing display information and other data to transfer, video takes precedence, so it doesn't start going like this. And also Thunderbolt provides 15 watts of power. Unless you switch over to power delivery, then it can do more. To actually get those signals switched over, we need a multiplexer that actually physically internally connects the Thunderbolt signals from PCI or the DisplayPort signals over. And if you want to know if a Type-C connector is Thunderbolt capable, there's a logo for that, and it should be on the plug and on the port. Some vendors are famous for not labeling any ports because it would disturb the industrial design. And yeah, so yeah, we'll see about that. There's also mobile high definition link. It's something that everybody has heard about, so I was told. This standard, it supports audio, video, USB 2 data, quite current data rates and signal rates and resolutions and that stuff. It does have a logo. I've never seen it before in my life. It comes in multiple variants. It has been changed the last time 2015, and it's never been formally finished to move on. It's only available on USB 3.1 connections, so legacy connections. It will never come to USB 4. And there's also no markings on ports or connectors that can do this. Some mobile phones do, very few laptops do, and they need a special MHL transmitter chip that mangles with the LCD panel data and HDMI signals to get that over. But you may want to try with your Android phone and a special cable. There's also HDMI. You know the HDMI. Yeah. And so do I. It was invented for use with home entertainment systems, TVs, projectors, and to replace older analog standards. It does have a logo. There's no signal conversion needed, actually, just the wiring, and you can have a Type-C connection with a HDMI plug on the other end, plug that in. HDMI version 1.4b is supported, so you will get full HD and stuff. It also does USB power delivery if you need, and the display capability info like DDC and consumer electronics control, like powering up your TV and shutting it down if you don't need it anymore, are also tunneled over the configuration channel. Again, alternate modes need a multiplexer chip for the signals. It's only available in USB 3.1, and it will not be carried over to USB 4. Connectors usually have either no marking at all or the HDMI link. Then there's virtual link. I see even more confused faces, like what? Is it a link or is it just, yeah. It was a standard that was supported by NVIDIA, AMD, Vive, Oculus VR, Valve, meaning the company behind Steam, and Microsoft. So this was especially invented for VR headsets. And it was never formally finished as a standard. There's only a single product on the market that I could find that would actually implement it. It's the PlayStation VR 2 headset for the PlayStation 5, and it uses a proprietary connector for that one. So I guess its market relevance is limited. And how do I know that? It does not have a logo. End of case. So alternate modes provide you with an ability to provide non-USB data over USB cables. They currently exist for USB 3.1 and 3.2 over Type-C, and the only really relevant ones are DisplayPort, which is the most used one, and Thunderbolt 3. Everything else has been deprecated. So, finally, moving on to USB 4. Why all that long lead up to here? Yeah, because we need all that foundational knowledge to understand what makes USB 4 special and what makes it actually pretty interesting and great. Because it's the first USB standard that mandates Type-C connectors. We remember, in the end, there can only be one. No support for Type A, Type B, none of the 14 variants, it's Type-C only. To be exact, Type-C revision 2.0 at least. It's very compatible with your existing devices. So it can do USB 2 data transfers, low speed, full speed, and high speed, all the way back to USB 2, USB 1.1. Why? Because it actually has those data pins on there. Like it's like physically the same. You can connect your old type devices. No, I will not plug out the adapter I have that I use for my control. I will need that. So if you have like an old iMac from the late 90s with a USB mouse and a keyboard, yes, you can connect those to a USB 4 port. Yeah, these are really awesome. You might want to have a look at the mouse and look at the details of that. Like, it really comes with the ball, it's not an optical mouse already. But you can connect it to a USB 4 port and it will work. It's also compatible with USB 3.2 data transfer speeds, like 5 gigabits in generation 1, 10 gigabits in generation 2. And it not only comes with a fallback to like 5 gigabits, it also does 10 gigabits. But wow, MacLemon, this is incredible. Where can I get this, and does it even more? Yes, it does. Optionally, 20 gigabits at generation 2x2. And it comes with an optional compatibility to alternate mode for DisplayPort and Thunderbolt. And if you order now, please call the number next to your flag. And provided your hardware actually supports this. So yeah, it does that. Free steak knives, anyone? No? Okay. So what else is USB 4 compatible with? Thunderbolt, explicitly Thunderbolt 3. Why is that? Intel donated the Thunderbolt 3 specification to the USB Implementers Forum as a foundation for USB 4, so they're almost the same. They can do the same things. And it's also aligned with the USB 4 and Thunderbolt 4 specifications, so those are like getting closer all the time. What's the difference between Thunderbolt 3 and 4? Well, one, obviously, I mean, it's basic math, you can do it. There's a lot that is the same, like maximum speed is 40 gigabits a second. It can provide 15 watts. Thunderbolt can do daisy chaining, like having elephants in a row, not in a room. And it does DisplayPort in multiple versions, and there are a few levels of compliance with the USB 4 specification. So what's different? Well, Thunderbolt 3 had a minimum bandwidth, like required by the standard, of 16 gigabits, a maximum of 40. And Thunderbolt 4 raised a few of those requirements, like the baseline was lifted up. The maximum specs are basically the same. And a few optional parts in Thunderbolt 3 have become mandatory. For a consumer, this is good because if you buy Thunderbolt 4 equipment, you get a little more and can be sure it actually does what you expect from it. But Thunderbolt also has a few limitations, like passive cables require a chip that does the signal conditioning for those high speeds, and that limits cables to, I guess, 70 centimeters, probably. Is that 70 centimeters? That's plausible, yeah. So what about USB 4? What are the building blocks that make up USB 4? Well, there's power delivery as a very basic foundation, a protocol that is needed for many other things. There's the Type-C connector and cable specification, because that is required. There's the USB 2 specification as a backwards compatibility layer way until the 90s. There's the USB 4 transport layer, and on top of that are sitting USB 3 again, there's PCI Express again, and DisplayPort as a possibility to be transported, and on top of it sits the compatibility with Thunderbolt. Not all of DisplayPort and Thunderbolt is also specified in USB 4, but they're aligned, and the next versions of Thunderbolt will also be aligned with the upcoming USB standard versions. So Intel and the implementers forum are talking to each other to make that easier. Power delivery, it's strictly mandatory for USB 4 operation. It establishes source and sink roles, as we have already heard. It provides VBus power, meaning powering your devices. It provides V-connection power, which is also mandatory. That is for powering the cable itself, or the plugs of the cable. And a USB 4 system will always prefer power delivery over fallback versions, like with 7.5 or 15 watts in alignment with the charging specification. Can't talk today. The configuration channel gets new assignments, not only discovery, but also entry and configuration of a USB 4 mode connection all over the power delivery protocol. And it also starts establishing lane 0 for USB 4 data transfers, and then upgrades to more lanes. We'll see about this in a moment. There's also the sideband channel is used for sideband transmit and receive. And USB 4 now also does host-to-host connections. What does that mean? Thunderbolt 3 already could do this. So you have a host, Alice, and another host, Bob. They want to exchange data. They have an operating system each that runs some bit of software, and you plug in a Type-C cable in between. With host-to-host communication, they're now able to have a virtual 10 gigabit Ethernet link over that cable without any adapters. Like, you don't need adapters to do networking. The software implementation for this will run simple IP. You get a virtual network interface like any other interface, and it will basically just work. So that is really comfortable if you want to connect two laptops together to transfer large amounts, like migrating from the old one to the new one. No need for Ethernet, you actually get 10 gigabits with this. What does the system architecture roughly look like? How do all those parts fit together? Well, we have the USCI. This is the protocol that a USB controller will talk to the operating system and tell it what has happened, what it can do. And at the bottom, we have the Type-C connector. So how do we wire this up? We have an embedded controller with a port manager. It talks to our system with that UCSI protocol. We have a power delivery and port controller. This is where that large state machine we saw earlier is actually implemented in. These are the components. It does come with a port termination that does the physical end and connects up, for example, to the CC wires. If that is all we have, we can talk configuration channel and detect plugging in of devices. If your device requires or provides power, we need the power management side. We've already seen that in detail. This is the simplified version. We wire that up to VBus, VCon, and ground, so we can actually provide power. Next, we want to exchange some data. So we need a USB data port with 2.0. We're directly hooking that up to the data ports for legacy connections. If we have an alternate mode capability in our device, we need more things. We need an interface that actually talks to this alternate device, like your graphics card or your PCI bus. And we need a multiplexer that can actually take the packets from those buses and mix them in with USB packets. Those are connected to the high-speed data pins on your Type-C plug. And Since we need the sideband pins as well, we need a sideband multiplexer, and that talks to the sideband pins. So now it doesn't look that scary anymore, I guess. I hope so, at least. But what happens if? Are there any fallbacks? I mean, something could go wrong. This is quite a complex system. And from a user's point of view, USB4 is quite nice with that. If your device can only do USB 3.2 or USB 2 speeds, it will fall back to those specifications and just basically work like you're used to. If your device has some USB 4's functionality and it can map that to a USB device class of the older standards, it should do that. Most of these devices actually do. So like a USB hub, a small one, will actually work at lower specifications. Of course, at a slower speed, but it will still work, which is usually handy when things, okay, it's slower, but at least it works now. And if it's not possible to map that functionality back because it requires some specifics, then yeah, there's this billboard class that at least should get you some error messages that you can use to find out why. And USB 4 requires all 4 data lines for that USB cable to be connected up. But what if you have an old USB cable that only has 2? Or it's been bent too many times, and it's broken. Only one pair works. Well, USB 4 will actually properly degrade that connection and work with 5 gigabits. It's slower, but hey, it still works. And it also works with older cables. So what do we get with USB 4 mode? We get something new. It's not alternate mode, it's protocol tunneling. USB 4 is packet-based, basically like IP is packet-based. And the nice thing is DisplayPort is packet-based, PCI Express is packet-based, and we can also take USB 3 signals and package them up nicely. So we can tunnel them over USB 4 fabric. So if you have these tunneled protocols, your host controller and device, they have a USB 4 router, which is that multiplexer thing, and it will take the packets from each of the buses and intertwine them, send them over the 4 fabric, over the cable, and at the other side they're taken apart, like this package goes here, this package goes here, this package goes there. And this is actually a very nice thing to make USB 4 future-proof. At the moment, all 4 USB 4 hosts support DisplayPort, and as far as I know, they support both modes, like USB 3 and 4 modes for alternate mode, meaning your old displays, like the new one you just bought with a USB Type-C connector, it will continue working in the future. And some of those capabilities, they are optional for hosts, they're optional for devices, but they're mandatory if you want to build a USB hub or docking station, meaning whatever your host will do, your docking station must be able to support. That is also one of the reasons why USB 4 and Thunderbolt 4 docking stations and hubs are really expensive, because they need to implement a lot of several 10,000 pages of standards and test all that. So that is hugely expensive to do, and that also affects the price of your final product. But you can be sure whatever you buy will work with whatever you connect to it in the future, because it's mandatory for these things to work. So what's coming up with USB 4 version 2.0? You've noticed there's no space in between USB and the number 4. That's for marketing reasons and trademark law. So it will be called USB 4 for quite some times, even if it's different versions of USB 4. Version 2.0 has been specified publicly like October last year, like just after BalCCon. It mainly extended this for power delivery 3.1 with extended power range up to 240 watts. So we're almost there. It also introduces new USB 4 data modes. We raised the limit from 40 gigabits to 80 gigabits. We double this by providing a new encoding that does 4 bits per cycle and not 2 bit, like a single bit per cycle, but 2 bits per cycle. And for DisplayPort, it raises the bandwidth from 2.0 to 2.1. DisplayPort 2.1 needs 77 gigabits a second. That is a lot of bits. For resolutions up to 16K in 10 bits color. And if you want to have multiple displays, USB4 will be able to switch to an asymmetrical mode, providing 120 gigabits down from the host and just 40 up. So you can have multiple DisplayPort streams down to your multiple displays and daisy chain them over. So that's quite interesting. And by cables, the question's always, how long? How long? Legacy USB used 14 different versions and with Type-C and variants of protocols. Well, how long can a cable be? Well, specification says the nominal length. Nominal being up to this length. If you're within what we specify as a minimum, you should actually end up with a cable that is capable of doing these speeds. With USB 2, there was 4 meters. With 3.2 Gen 1, that's 5 gigabits, you get 2 meters at least. USB 4 generation 2 is also 5 gigabits, it does 2 meters. And the higher the speeds get with the generations, the shorter the cables become. Well, there's this beefy USB Type-C cable that we started giving out. If you look at the labels on those connectors, it says 40 gigabits at 240 watts. And that cable is not 0.8 meters long, it's 2 meters. So you can go over this if you have a quality cable. And we've seen the two cross sections, the different ones. One looked significantly more clean with coax stuff than the other one. So that's also the reason these cables are capable of doing this. They get certification, so they can prove it actually works. They have an e-marker that tells you that this actually works. You can test it, and it really works. So that is nice. But the specification is very conservative with cable lengths. But with a good cable, which is expensive, you can get there. So a Type-C to Type-C cable is like a box of chocolates. You never know what you get. It's basically possible to see what a cable can do. So you need a testing device, and testing is complicated. There's many different on the market. You can get non-Type-C things like these for $10 online. There's more expensive ones like this FNB58, which can do Type A and Type C. It's probably the device with the most weird USB plugs you've ever seen. That's around 60, 70. And for professional equipment, like industrial capable things, you can easily pay like 15,000 or more. But you're unlikely to get one of those. So I recommend you get yourself one of these. This is a Power-C device, and you can use that to debug a Type-C connection because you can just inline it with whatever device you have, and it will tell you what actually happens on that connection. I'll hand out those two. I want them back. I really want them back, yeah, please. The software interface you can also use to introspect and interrogate your cable because the host uses it. The specification is by Intel. On Windows, you can use UCSI control.exe. It will help you tell you what Windows thinks that the cable can do. If you're using Linux, there's the USB Type-C connector class. It's a structure in the kernel that you can query. It may or may not have information on that port, depending on your distro flavor, version, and the moon phase. It tells you like what is me, like the first port, it's zero-based array, like arrays should be, unless you're Lua. It tells you what the port cable is and what the plugs on the cable are, like on the close end and on the far end. And if your cable has an e-marker, you can query the first e-marker with a start of packet prime query that queries the first e-marker. If the cable has more, you can query the other e-marker with a standard of packet double prime message, and it will get you that information as well, because there's cables that only have one, there's cables that have two. And there's cables that have fiber optics in between, and you need to find out which is one So depending on the cable and your Linux, you can see if you find out what these are. I really recommend getting a testing device because those will make sure and are easy to operate. Yeah. Type-C allowed cable lengths. The ones I gave you are for passive cables with copper. With optical ones and active cables, you can go longer. They have repeaters and signal conditioning and signal retimers in them. They can become very expensive as well. So a few conclusions and learnings from all this madness. It's like literally tens of thousands of pages of specification. It goes into many details. But I had to like really go into like, oh, how does ST Electronics or Texas Instruments or Cypress actually implement a protocol multiplexer to find out a few things that are not really clearly easily found to be found in the specification. So Type-C plug rotation independence, like flipping it around and it still will work. Well, it's not physically rotation independent as we've seen because the data plus and data minus pins, they're only on one side and the other one's empty. The configuration channel is only wired up on one side. But the multiplexer on your port should handle that. It's exactly to do these things and provide rotation independence. And when all the parties and port partners comply with the specification, it is rotation independent for the user's point of view. From an implementer's point of view, you need to take care of that. That also means if you handle rotation in your plug, you can also deliberately handle it differently because you like to do so. So if you want to build a USB Type-C thumb drive that behaves differently if you plug it in this way or if you flip it around, it can, huh? Yeah, you can provide like the other half of the flash memory you actually have and provide a different data partition. If you put a capacitor on there, you can take memory like I've been plugged in this way, then I've been flipped around, and then I've been flipped around again like a proper type A connector should have been. And only then you will show the correct data partition. Ah, that is evil, huh? So yeah, there may or may not be people who have been at BalCCon who have working and implementing these shenanigans. But yeah, you can have a lot of fun with those. You may also remember from 2016, a Google engineer bought up like all the USB Type-C cables they could find on a popular like smiling retailer online. And some of the cables like literally burnt out Chromebooks because they had power pins connected where they should not have been connected. So they clearly did a strict testing run of those cables. I guess they were up to like 3 Chromebooks going up in flames by testing tons of those cables. We're happy that those times are gone. Like power cables, Type-C cables you can buy now, they do not have those issues anymore. So even if you buy them on AliExpress or so, you get cables that at least do something except burning down your house. The present future of this USB thing, the future is now. USB here, USB4 is already here. The value of USB is in the application that it allows, and it's here to stay. It fundamentally changes how USB works by like moving from a circuit switched type of connection with USB 3 where you dedicate the lines explicitly and like really do different signaling with different voltages on the same wires to a packet-based system, like a packet switched system, and that future-proofs it for future protocols. Like now you can do Thunderbolt and DisplayPort and PCI. You could wrap other protocols in packets and move them over a USB 4 fabric. So that future-proofs that technology, but it's still backwards compatible with the last 25 years of USB. Like USB is not a teenager anymore. Huh? Also nice, all of the specification is available from the USB Implementers Forum. It's available for free. It's tens of thousands of pages of huge PDFs. They come with diffs. They come with marked diffs, the so-called red line versions, where everything that changes is underlined in red or struck out in red. So you can see what has been changed from the last revision. And if you get the last one, it will always contain all the changes of before revisions. So you get the current thing that's actually valid at the moment. To reduce complexity for implementers, there's many ready-made things like USB trigger boards that you can use for your own projects or for building a commercial product. Please make use of those. They make your life a lot easier and will make debugging a lot easier. So with USB4 version 2.0, you know it's been out a year already. It takes usually between like 12 and 18 months for devices to appear on the market. It comes with 80 gigabits of transfer speed on USB 4 mode over the same cables that you used for USB 4 generation 3. Like the 40 gigabit cables, they're by standard physically identical. May you get 80 gigabits over that old cable? It depends. It depends on 3 bits. Those 3 bits in the eMarker chip tell you like, hey, we can do 40 gigabits. And the host needs to know, like the old standard with 40 gigabits can actually do 80 gigabits in the new one, and I will overwrite those 3 bits that tell me, well, it's a generation 3. And if you need a generation 4 cable for 80 gigabits and the host says, well, the cable does not explicitly tell so, you need to buy a new cable with 3 bits flipped in a chip. It's physically the same. So that would be interesting. But more high resolution to drive your displays. What else is there? The EU Universal Charger Directive. It's formerly called Radio Equipment Directive. Basically, everyone calls it Universal Charger. It mandates Type-C as a connector by the end of 2024, by the end of next year, as a charging means for all small electronic devices. Laptops get a little more leeway until 2026, but with extended power range, we get 240 watts, so even if you have a ThinkPad W540 something monster or a gaming laptop or an electric scooter, yes, USB Type-C will be able to do that. And also expect more very popular small devices to become and switch to USB-C connectors this Tuesday at a marketing event by a large Californian computer retailer. There's also an environmental impact, not only for for EU member states, but all over the world, because device manufacturers will not provide a USB Type-C device for the EU and another one for the rest of the world. I mean, they're not that stupid, they're greedy, they want to earn money, and making things simpler for them makes them more money. For you, that also means a personal impact, like you can travel with a single charger that can power your laptop, can charge your phone, can charge your smartwatch, your portable gaming console, and whatever you like. So your scooter, if you brought one, I did forget, it was a stupid idea to not bring it. So your luggage may become lighter, not light enough to fit in an overhead compartment of an airplane, but it's a good thing. And more shenanigans with testing USB cables. So that concludes the infinite topic of USB. Thank you to all of the BalCCon team who provided me with ideas by putting up a table, helping me with stupid things, giving me a chance to talk to somebody for an hour about how do I convey this information so that you actually get something out of it. You were a huge help, thanks to many other ones. I've listed a few that have put up with me and my foolish endeavors to talk about USB. If there are questions, I've already been signed that there's no time. My timer says there's 20 seconds. So if you still have questions, please come to me after the talk. I can show you these testing devices, what they can do, what they can tell you, how they work. Please bring your USB Type-C cables, and if you want to find me online, I'm on the interwebs and at the conference for the rest of the day. Thank you very much.